Welcome back to a new session of the MOOC on Information Security. Here we will discuss digital signature. The objectives of this module are to provide an overview of the process of digital signature, to understand the services and schemes, and to get an idea about the attacks on digital signature. Have you clearly identified the importance of a signature in our day life and day-to-day transactions? Simply, it is identification. In order to transfer funds from one person to another, to make sure on the person who issues some notices or orders everywhere, we need a signature which certifies the validity or concern of the person who signs in it. Just think of a parallel situation. In electronic transactions, we need a method to confirm the authenticity just as the conventional paper mode. Suppose Tina sends a message to her bank authorizing it to transfer 25,000 rupees to Jia. Then the bank should verify and prove that the message was originally sent by Tina and also the message has received correctly without any alteration along the way. But this process is a bit complicated in electronic transactions instead of paper. There comes the digital signature, which is a protocol to produce the effect of a normal signature. This mark is made by only the sender and the other people can easily recognize it as belonging to the sender. Thus, it confirms the agreement to a message. Properties of digital signature. A digital signature should meet two key properties. It must be unforgeable. If a person X signs message M with signature S of XM, it is impossible for anyone else to produce the pair M S of XM, and it must be authentic. If a person R receives the pair M S of XM apparently from X, R can check that the signature is really from X. Only X could have created this signature and the signature is firmly attached to M. It is not alterable. After being transmitted, M cannot be changed by S, R or an interceptor. It is not reusable. A previous message presented again will be instantly detected by R. The first two requirements are the major difficulties in computer transactions. Hence, to create a digital signature, we must present a mechanism that meets all of the above said requirements. To clearly understand the working of a digital signature, we need to have a clear idea about the following concepts. We have studied some of them in our previous sessions and you will get details of the remaining in the coming sessions. Anyway, we will have a quick visit. Hash function. A hash function, also called a hash, is a fixed length string of numbers and letters generated from a mathematical algorithm and a randomly sized file such as an email, document, picture or other type of data. This generated string is unique to the file being hashed and is a one-way function. A computed hash cannot be reversed to find other files that may generate the same hash value. Some of the more popular hashing algorithms in use today are Secure Hash Algorithm 1, SHA-1, the Secure Hashing Algorithm 2 family, that is SHA-2 and SHA-256, and Message Digest 5, which is MD5. Public key cryptography. Public key cryptography, also known as asymmetric cryptography, is a cryptographic method that uses a key pair system. One key called the public key encrypts the data, the other key called the private key decrypts the data. Public key cryptography can be used several ways to ensure confidentiality, integrity and authenticity. Public key cryptography can ensure integrity by creating a digital signature of the message using the sender's private key. This is done by hashing the message and encrypting the hash value with their private key. By doing this, any changes to the message will result in a different hash value. And it can ensure confidentiality by encrypting the entire message with the recipient's public key. This means that only the recipient who is in possession of the corresponding private key can read the message. Verify the user's identity using the public key and checking it against a certificate authority. Public Key Infrastructure or PKI. PKI consists of the policies, standards, people and systems that support the distribution of public keys and the identity validation of individuals or entities with digital certificates and a certificate authority. Certificate Authority or CA. A CA is a trusted third party that validates a person's identity and either generates a public or private key pair on their behalf of associates an existing public key provided by the person to that person. Once a CA validates someone's identity, they issue a digital certificate that is digitally signed by the CA. The digital certificate can then be used to verify a person associated with a public key when requested. Another one is digital certificates. Digital certificates are analogous to driver license in that their purpose is to identify the holder of a certificate. Digital certificates contain the public key of the individual or organization and are digitally signed by a CA. Other information about the organization, individual and CA can be included in the certificate as well. Pretty Good Privacy PGP or Open PGP. PGP or Open PGP is an alternative to PKI. With PGP or Open PGP, users trust other users by signing certificates of people with verifiable identities. The more interconnected these signatures are, the higher the likelihood of verifying a particular user on the internet. This concept is called the web of trust. Working of a digital signature. Digital signatures, like handwritten signatures, are unique to each signer. Digital signature solution providers follow a specific protocol called PKI. PKI requires the provider to use a mathematical algorithm to generate two long numbers called keys. One key is public and one key is private. When a signer electronically signs a document, the signature is created using the signer's private key, which is always securely kept by the signer. The mathematical algorithm acts like a cipher, creating data matching the signed document called a hash and encrypting that data. The resulting encrypted data is the digital signature. The signature is also marked with the time that the document was signed. If the document changes after signing, the digital signature is invalidated. As an example, Tina signs an agreement to sell a timeshare using her private key. The buyer receives a document. The buyer who receives the document also receives a copy of Tina's public key. If the public key can't decrypt the signature via the cipher from which the keys were created, it means the signature isn't Tina's or has been changed since it was signed. The signature is then considered invalid. To protect the integrity of the signature, PKI requires that the keys be created, conducted and saved in a secure manner and often requires the services of a reliable certificate authority or CA. We will see the working of PKI in detail in a future session. Approaches of digital signature. A variety of approaches has been proposed for the digital signature function. They fall into two main categories such as direct and arbitrated. Direct digital signature. The term direct digital signature refers to a digital signature scheme that involves only the communicating party's source and destination. It is assumed that the destination knows the public key of the source. Confidentiality can be provided by encrypting the entire message plus signature with a shared secret key, which is symmetric encryption. Note that it is important to perform the signature function first and then an outer confidentiality function. In case of dispute, some third party must view the message and its signature. If the signature is calculated on an encrypted message, then the third party also needs access to the decryption key to read the original message. However, if the signature is the inner operation, then the recipient can store the plain text message and its signature for later use in dispute resolution. The validity of the scheme just described depends on the security of the sender's private key. If a sender later wishes to deny sending a particular message, the sender can claim that the private key was lost or stolen and that someone else forged his or her signature. Administrative controls relating to the security of private keys can be employed to thwart or at least weaken this ploy, but threat is still there, at least to some degree. One example is to require every signed message to include a timestamp, date and time, and to require prompt reporting of compromised keys to a central authority. Another threat is that some private key might actually be stolen from X at time t. The opponent can then send a message signed with X signature and stamped with the time before or equal to t. The universally accepted technique for dealing with these threats is the use of a digital certificate and certificate authorities. Arbitrated digital signature. The problem associated with direct digital signatures can be addressed by using an arbitrator. Hence, the arbitrated digital signature includes three parties in which one is the sender, the second is a receiver, and the third is the arbiter, who will become the medium for sending and receiving messages between them. The message is less prone to get corrupted because a timestamp is included by default. Every signed message from X to Y goes to an arbiter A that everybody trusts A, checks the signature and the timestamp, origin, content, etc. A dates the message and sends it to Y with an indication that it has been verified and it is legitimate. Example, every user shares a secret key with the arbiter. X sends to A an encrypted form of the plaintext P together with Y's ID, a timestamp and a random number RA. A decrypts the message and thus makes sure it comes from X. It also checks the timestamp to protect against replays. A then sends Y the message P, X ID, the timestamp and the random number RA. He also sends a message encrypted with his own private key that nobody knows containing SID, timestamp T and the plaintext P or a hash. Y cannot check the signature but trust it because it comes from A. He knows that because the entire communication was encrypted with the key of A, which is KA. Y will not accept old messages or messages containing the same RA to protect against replay. In case of dispute, Y will show the signature he got from A, only A may have produced it and A will decrypt it. Here, the arbiter is in a position to prevent fraud on part of either X or Y, but the arbiter could form an alliance with the sender to deny a signed message or with the receiver to forge the sender's signature. This problem can be solved by using a public key scheme. In this case, X double encrypts the message M first with X private key PRX and then with Y's public key PUY. This is the signed secret version of the message. This signed message together with X identifier is encrypted again and sent to A. The inner double encrypted message is secure from the arbiter and everyone except Y. However, A can decrypt the outer encryption to assure that the message must have come from X. A checks to find that X key pair is still valid and verifies the message. Then it will be transmitted to Y, which includes the double encrypted message and a timestamp. The advantages of this scheme include no information is shared among the parties before communication, preventing agreements to defraud, and no incorrectly dated messages can be sent, and the content of the message from X to Y is secret from A and anyone else. Attacks on digital signature. Attacks and forgeries as listed by Gold 88 list the following types of attacks in order for increasing severity. Here, A denotes the user whose signature method is being attacked and C denotes the attacker. Key only attack. C only knows A's public key. Non-message attack. C is given access to a set of messages and their signatures. Generic chosen message attack. C chooses a list of messages before attempting to break A's signature scheme, independent of A's public key. C then obtains from A valid signature for the chosen messages. The attack is generic because it does not depend on A's public key. The same attack is used against everyone. Directed chosen message attack. Similar to the generic attack, except that the list of messages to be signed is chosen after C knows A's public key, but before any signatures are seen. Adaptive chosen message attack. C is allowed to use A as an oracle. This means that A may request signatures of messages that depend on previously obtained message signature pairs. In the paper, Gold 88 then defines success at breaking a signature scheme as an outcome in which C can do any of the following with a non-negligible probability. Total break. C determines A's private key. Universal forgery. C finds an efficient signing algorithm that provides an equivalent way of constructing signatures on arbitrary messages. Selective forgery. C forges a signature for a particular message chosen by C. Extensional forgery. C forges a signature for at least one message. C has no control over the message. Consequently, this forgery may only be a minor nuisance to A. Digital signature requirements. Based on the properties and attacks discussed here, we can formulate the following requirements for a digital signature. The signature must be a bit pattern that depends on the message being signed. The signature must use some information unique to the sender to prevent both forgery and denial. It must be relatively easy to produce the digital signature. It must be relatively easy to recognize and verify the digital signature. It must be computationally infeasible to forge a digital signature either by constructing a new message for an existing digital signature or by constructing a fraudulent digital signature for a given message. It must be practical to retain a copy of the digital signature in storage. A digital signature is an electronic encrypted stamp of authentication on digital information such as email, messages or electronic documents. A signature confirms the authenticity of the sender and the message, or in other words, that the information is originated from the signer and has not been altered. This module describes the digital signature, its properties, working, requirements, types of signature and the attacks possible on them. Hope you enjoy this session. See you next time. Bye.